Inviting Deltares, me and my colleague Minder, to this session. Well, as a champion user, maybe also a prospective champion user, I would say. I'll give an introduction to Deltares and to a few use cases that we really are using or can make good use of the CMEMS services. And my colleague will continue on that to focus towards the coastal applications. I will focus more on the offshore applications. And maybe, well, I'll come back to that as a title. We were focusing on not only the marine monitoring, but also I'll highlight a few other examples. In that sense, I'll push this one aside. I'll give a short introduction to Deltares. We're a Dutch not-for-profit research organization. We're doing applied research on a lot of things that do with water and the subsoil. It's a very Dutch, as Cora van Nieuwhuis also introduced, a Dutch issue, but we're also making this very international. It's how to manage your low-lying delta regions worldwide in a safe and sustainable way. We have about 800 employees in two main offices in Delft, close to The Hague, and in Utrecht, in the middle of the country. And we have a couple of branch offices around the world that also link to international projects. I think 1/3 of our work is governmental focused, so for local and national governments. We have a proportion of work we do for the private sector as well as national as well as international, and there's also NGOs for which we do a lot of projects. Thematically, we have 5 themes that connect the work that we do. So we work in regions like the offshore, the inland waters, the subsoil, but there's a strong linkage with thematic orientation of our organization. In particular, for the presentation of today, it's the flood risk and the sustainable delta planning, as well as the ecosystems and environmental quality that are of relevance. But also the other do matter, of course, for application of space data and technology. Within the Copernicus services in general, I think Deltares is an interested user. We're already using some data from different resources from the sentinels, the different sentinels, to build this or to transform this data into useful information products. Tools, models, forecasts, that's what we do. And in this value chain of going from core data in the ground segment to Copernicus service to added value services, we have our focus in this added value service, but I dare say we have the ambition and the interest to expand it also towards the user side, but also towards the upstream part of the Copernicus. For marine services in particular, I'll give a few examples in my next slide. But these are mostly focused on marine, but also some inland water quality applications. The different EU projects and national projects where we collaborate and develop, say, downstream products or more in the core, like the MyWave project products. So for one of these cases that I just showed, the NEFREF project is a national project with our partner, the Delft University of Technology. We actually use data from the Copernicus service to improve the reference levels of the vertical datum in the Dutch system. There's a European system of referencing vertical water levels, very important for navigation, but also for dike and coastal safety. And we can use models for this, but we also use satellite data, gravimetry data, but also model data from others. So the model data from the NEMO model in the CMEMS portal does contain density information, and density, say lighter water compared to heavier water to denser water, will make a difference on the total water level that you find in the ocean, but also in the shelf seas. So you see here an example of what we then call the mean dynamic topography. This is with respect to the equilibrium of the gravity field. Say relatively lighter water, that's also influenced by river outflow. Fresher water will stand up higher. There will be a bulge of water of a few centimeters to decimeters. And to have this accurately computed, we do our own computations with regional scale modeling, but also manage to include the Copernicus data. So this is really an added value of a good quality of data. Another application is more in the maritime sector, in the offshore sector, Metocean. Here we use our FEWS system. FEWS is an open platform software system that's open to actually any sort of model and data stream to combine this into operational forecasting systems. And here it's a forecasting system for the offshore wind sector. They in particular want to optimize their operations and maintenance. Seeing that 30% of the price of an offshore kilowatt hour is determined by the operational costs, there's a possible business case to make this more effective and efficient. So they want to know more precisely the wave conditions, the wind conditions under which they can operate. And this is clearly an example where I think in the future we can really benefit from the wave data, for example, that's being published in the next year's upgrade of the Copernicus service. So with the FEWS software, what we now do, and actually we do this worldwide with this software package, we build a regional scale model. It needs boundary conditions. Those boundary conditions we can excellently get from the Copernicus models. For the currents, for the water levels, and in the future for the waves. And in that sense, once we have this, we make something of a user-friendly interface to, well, a wind farm operator in this case, to provide them with an operational window as precise as possible. Say your wave levels will be like this, your periods will be like that, and your currents will be like such. And with this interface, the operator can look for the best strategy to survey or maintain its park. And also here we're looking for new, say, extensions to the traditional Metocean. It's not only the waves and currents, but potentially also water quality parameters. And in particular, when you think of a multifunctional use of wind farms, also for offshore aquaculture, it's possibly interesting to also have chlorophyll data, for example. So we're developing on that one, which gives me a bridge to aquaculture information services in general. And the Aquaculture project, Deltares, with a lot of partners, is working on focused case studies for the aquaculture sector. And here, the algae blooms are an important issue, of course. Harmful algae blooms can negatively affect, say, the harvest of mussels or the fish or salmon. So you want to know, as an owner of such a plant, is my plant at risk? And with aqua users, there is spaceborne data like chlorophyll, temperature, and suspended solids being combined with meteorological data being aggregated and validated also with ground truthing observations, and in the end also being published in a portal giving information to an aqua user, an aquaculture user. And this is again the bridge to more wider scale marine environmental monitoring for the water framework, the Marine Strategy Framework Directive, which we're doing on behalf of the Dutch Ministry of the Environment, with the agency Rijkswaterstaat as the responsible agency to carry out the monitoring. And in fact, Rijkswaterstaat is interested in the question, or they're posing us the question, can we do it more efficiently, cost effectively than we do right now? And can we use Copernicus data for this? So we're evaluating actually different scenarios with them. And one of the, say, possibly low-hanging fruits is of course to use the ocean color data from Copernicus. So we're currently evaluating this and we see great potential. In the end, it's also like Rijkswaterstaat, director of the water management sector, Roland Allerlijn. He said, yes, we're at the edge of using it, so why don't we just start using it? And I think we can make a great opportunity out of this. It's very good for not only our short-term efficiency, but also for getting knowledge and learning what to do. So the Marine Strategy Framework Directive is really aiming at a good environmental status, and it's more than just ocean color. This is like a report by the Environment Agency on the status of fisheries. Is it sustainable, yes or no, for different regional seas? But there's, say, 11 indicators that matter, descriptors that matter for the Strategy Framework Directive. But some of them are quite intensive to determine, like contaminants in the sea and eutrophication, which is descriptor 5. That's the level of algae actually. So eutrophication is caused by excessive runoff of nutrients into the water, which causes excessive growth of algae, which is not only potentially harmful for shellfish, but also for the total ecosystem. It's not always bad, high algae blooms, but it can be bad. So there is a whole framework of assessment. Say, when is it too much? It's a combination of factors. High inputs of nutrients in particular seasons, high growth of the algae in other seasons, shifts in species, particular algae species that can be of a nuisance. And in particular, when the algae die, they consume oxygen, and oxygen can be so low that shellfish, for example, can die. This is really an adverse effect that people want to avoid. So these parameters, they go into an indicator. It's one of the indicators for the Marine Strategy Framework Directive. But to determine these, you have to go out quite often to sea, for example, because the algae blooms can be very local and high in short time period of time. So how do you catch this when you go out with a ship? This is the traditional way of measuring. When the Rijkswaterstaat ship, which is one of these, goes out to these red dots. For example, 4 times a year it goes 300 kilometers to the north in the Dutch continental shelf. So it goes all the way there to collect a few of these bottle samples and take them to the lab. Is this enough data to draw a conclusion about? Can we tell that the ecosystem is getting better or not from these sort of data? And how effective is our policy actually to reduce the nutrients in this case? Can we do this differently? This is the context where we're talking about. So we're thinking of integrating not only ocean color data, but also different ways of measuring with instruments that do it automatically. So you have to weave a structure where you say, okay, I got a spatially covering remote sensing image, or an aggregate, like a temporal mean, which you can easily derive from it. I can still got my shipborne samples, but I can also have transects with a ferry box, which is an autonomous system on the third-party ship, and integrate it into a more effective way of sampling. So then you get numbers that you really can make sense out of. And this is an example of such an approach where we have pre-Copernicus MERIS ocean color data. And you see the red line is the trend, and the upper part is the trend by traditional data, which is these in situ samples. If you take the samples from a remote sensing satellite at the same plot, or the same dot, you get roughly the same trend. But if you get the data from a whole spatial pattern, from a whole spatial patch, which is this pink patch, you get a different picture. And that's because of biases in the location of these dots. They're not at representative locations. So this is one of the differences that we're evaluating with the Rijkswaterstaat. And in this sense, it's also interesting to know, of course, that in the end, the water quality assessment improved, but it could also be the other way around. But this is important to know. So this is an assessment that we're making with them. So just due to a better representation of your data from space compared to in situ data. So when remote sensing chlorophyll fully or partially replaces seaborne data, we see a lot of benefits. So we get a smaller error in our sampling and an assessment. And it could be that the data, like in this middle bullseye, they're less precise maybe per sample, but we get so many more samples that the average is still better. So it's more accurate maybe than a few bottle samples that might be biased. So there's one, but there's another benefit from it. It's also that we have some commonly accepted data. It's international data. And there's also an issue in the collaboration with countries around us. We want to do this monitoring not on this triangle at sea, but to do it together with the Germans, the Belgians, and the English. And sharing a common data set is also good for harmonization of the levels that we apply to. So it's a coherent assessment at a larger scale than just this triangle of the Dutch waters. And a different role of the agency, actually going out to sea is still required, but you do it in this integrated framework of sensors, and you focus on validation of the data. And this is also changing in the minds of the operational surveyors. We're taking time for that. So this is clearly, well, an outlook that we really appreciate. To give a final slide on a bit of wishes from our users, actually the government users, for this sort of application. And what is important for them is that they are able to have the lineage of the data product, so to refer back to the source of the data and the version of the data that's been used to make this particular assessment reported to Brussels. If the data changes at the source and they're not sure on the quality of the assessment, they want to be able to get back to the original data. So this is a matter of version control or documentation. They need insight. This is a little bit my remark of this morning, so validation of the different levels of the products. Also composite products, how are they made and how can I get trust in it? There's also issues on consistency in time when you switch from one sensor to another one or you upgrade your algorithm. How to deal with this? I think we'll tomorrow have a session with the providers from Belgium. We have this sort of discussion. And also, it's not always critical for them to have the best product, but they want an acceptable product. It can be a compromise product, so acceptable product at a larger region might be better than the scientifically most advanced product. So this is also something to take into account. So I hope this is a nice piece of information for you. You're welcome.
Thank you.